Same procedure that we did in a prior problem. I mean, what we're going to do is we're going to calculate the entire molecular mass for this compound, this formula as written, and then we're going to figure out what the total number of each element has mass would be per mole, and then we're going to just divide it, each of those per mole element masses by the total mass. Probably easier to show you than saying incredibly confusing and convoluted words. Okay, so let's figure out how many of each element there are in this formula. Okay, so let's figure out what the counts are in the formula. How many sulfurs are there in this formula? 1. Yeah, exactly. So there's nothing written here, so that's an implied 1. So 1 for sulfur. For oxygen, how many oxygens are there in this formula? 4, right. So 4 there, great. That's what this 4 refers to. It comes right after the O, so it refers to whatever came to the left of the subscript. How many different CH3 groups are there total in this formula? There are 2. So each of these CH3s, there are 2 of them. That's what the parentheses mean. That's what that 2 is referring to. It's everything in parentheses. So since there's 1 carbon inside of this methyl group, and there are 2 of them, how many carbons are there? Excellent. 2. And then how many hydrogens? 6, right. 2 times 3 is 6. Okay, so now we're going to have to figure out what the atomic masses are for each individual element. You go to the periodic table. For carbon, that's 12.0107. Great. 12.0107. For hydrogen, what's the atomic mass for hydrogen? Right, it's 1.00794. It's the nasty number at the bottom that is the decimal answer. And most of the time, that's what you're going to get is some nasty like decimal answer that's like an average of the different isotopes that are present in the Earth's crust. However, let's go down to something like seaborgium. How would you know what the atomic mass of seaborgium is? All right, so if somebody said bottom number, I'll allow it. That's a great answer. It's the number that's in parentheses. It's a great answer. It's 271. What if somebody didn't put it in parentheses? What if you just had to choose between 106 and 271? Which one would you pick and why? You'd pick the 106, right? Or sorry, the 106 is the atomic number. It's the number of protons. You'd pick the 271 as the mass. But how could you tell which one you'd pick? Is it always going to be the bigger number? Is the mass always going to... Yeah, it's going to be the bigger number because it's got... The mass has neutrons and protons in it, regardless of how I stutter and make mistakes in my speech. Whereas the atomic number, the 106, is always going to be smaller because it's just the count of the protons. So even if someone had scrambled the order or reformatted this thing and made it in some weird postmodern format where, like, the mass numbers, you know, written vertically up the side and the atomic number is, like, diagonal, you could tell me that it's going to be 271 because 271 is bigger than 106, and you know there's going to be more protons plus neutrons as a number than just protons. Also, another clue here is that if you just look at the format of the periodic table and you go, hey, what's the difference between the previous element and the next one over? Well, it's going to be a change of 1 atomic number because there's just a change of 1 additional proton that corresponds to the change in 1 higher atomic number. So if I just look at the formats here, I can see that from going from dubnium to seaborgium, and no, I don't think dubnium was named after the ex-president, but that's kind of funny. So like, from going from 105 to 106, that's a change of 1, whereas going from 268 to 271, that's not a change of 1, that's a change of 3. So when we're looking for a change of 1 extra proton, clearly it's 105 to 106, not 268 to 271. Apparently when you go from this isotope, you have an additional 2 neutrons, an additional 1 additional protons. That's why it goes up by 3. Okay, so for hydrogen, it's going to be 1.00794. And for sulfur, we can look that up also. So sulfur, 32.065. So far, so good. And then for oxygen, it's like 15.9994 or something. Let's check that out. Yep. Okay, so we got that. So what I can do is I can multiply the count times the atomic mass and figure out what the total mass is for an element, like all of that element. So both carbons give me 24 atomic mass units. And if I just repeat this all the way down and multiply count times atomic mass, I end up getting this product. So those 6 hydrogens have about 6 AMU. And I do it for all the different elements. And then I sum them up. So if I add up all those products together to get the total mass from all the different elements in their full counts, I end up getting that it's 126.132 atomic mass units or so. And then if I want to figure out what the percent contribution is for every element, I just sit there and go, okay, this is the mass from the carbons. If I divide it by the total mass, I will get the percent mass contribution of those carbons. So that's what I do. I divide this number, the mass from just the carbons, by the mass from all the other elements together, including the carbons, and I get 19.04%. Okay, so I can repeat this and divide. So like, for example, here, I'm just dividing the mass of the oxygen by the mass of everything. This is the molecular mass of the molecule, or the formula at least, and this is the just the mass of oxygen itself, all those oxygens, 4 of them together, divided by the total. And that gives me about 50%. So if you had to write this stuff down in a computer program, what I would recommend you do is, figure out what either sig figs they want you to round to, or what places they want you to round to that might have specific instructions. Do that for the smaller contributors. And then if they ask for like the last one, I would just subtract all these rounded answers from 100, and I would put in the result of that. You want it all to add up to 100, and right now there's clearly a rounding error because you can't add a bunch of even numbers to plus 1 odd to get an even number. So I'll show you what I mean by this. So 19.04, 4.79, 25.24. So these are like the smallest contributors, so I would not mess with these numbers. I would not try to make them distorted at all, because if I have a change in a number here, it's a much bigger change. Like a hundredth of 4.79% is a much bigger difference than a hundredth of 50.74, sorry. So what I'll do is I will just subtract all this stuff from 100. So 100 minus that, minus that, minus that. So,
it's 25.42.
uh-oh. So I love Excel because I make mistakes. Okay, so here I have these numbers. When they're rounded, they add up to 100. These don't quite add up to 100, so that's what I would do. And that's basically it. So if you have to troubleshoot an answer, that's the next thing I would do beyond just rounding everything independently.